Hi guys, Miss O'Connell here. So the last form, which was labeled Intro to Uniform Circular Motion, exit ticket, about 12 of us out of 60 did not complete it. So that's the highest number yet so far this year. So that's about 20%. So because about 20% of us had issues with this form, I'm just going to go over the two questions in this video. Okay, so again, that form is called the Intro to Uniform Circular Motion Exit Ticket. There were two questions. Those questions are based on the combination of the two videos, one which was from Edpuzzle, and then a series of examples that I had recorded. So again, you can find this in Classroom. So let's talk about the two examples. So the first one you can see is on this yellow sticky note here. So we have a 2-kilogram ball on a string, which is rotated about a circle with radius of 10 meters. The maximum tension that the string can withhold is 50 newtons. So anything larger than 50 newtons would cause a string to break. Okay, so 50 is the maximum tension on that string. We want to find the maximum speed of the ball. Okay, so this example is similar to the example video 1 in which I recorded. So first thing that we do here is we draw an image to help us visualize what is going on. So we have here an object like a ball attached to a string, and that object is rotating in a circle. Right, the radius would be the length of that string. And we're told that that radius, is 10 meters. Okay, so the length of the string, aka the radius of the circle, is 10 meters. And then the object, the ball, that is attached to that string, it has a mass m of 2 kilograms. We're told that the maximum tension that string can hold, T, is 50 newtons. We want the maximum speed of the ball. So we're asked for maximum speed in uniform circular motion. We are talking about the tangential velocity, which is the velocity of the object tangent to, tangent to the circular path. So tangent means that there is a 90-degree angle between the path and the tangent line. If the string were to break, that object would move in a straight line along that velocity vector. So we're going to figure out what that maximum speed is. So we need to take what we know, use the circular motion equivalent of Newton's second law. We know that objects move in a circle because of a constant center-seeking force, which we call the centripetal force, F sub c. It's a net force, and in this case, right, that centripetal force is the tension. Okay, it's the force that causes the object to move in a circle, which here, of course, is our tension. We know that the sum of the forces, or the net force, must be equal to mass times acceleration. In this case, right, if it's a net centripetal force, it's going to give us our centripetal acceleration. Okay, so we know that the tension is equal to the centripetal force, so we can plug that in for the tension, or for the centripetal force, rather. So F sub c is going to be equal to the tension. The mass of the object we know is 2 kilograms. Okay, and the acceleration, we don't know what the acceleration is, so we're going to need to solve for that. Okay, So we know our maximum tension can be 50 newtons. We're going to plug in 50 for T. And 2 kilograms for the mass. And we're going to solve for the centripetal acceleration, which is the center-seeking acceleration of the object as it moves around that circular path. So we divide both sides by 2, we're going to get 25. Our units are meters per second squared. Okay, so now that we have the acceleration, we are not done, right? We need to find the maximum speed. Okay, we know that the speed and the acceleration are related to each other using that equation, which was mentioned both in my video and in the Ed Puzzle video. Oh, wrong eraser. Oh, there we go. Clean that up a little bit. Okay, we know the centripetal acceleration is equal to the tangential velocity squared divided by the radius of the circle. Okay, and lucky for us, we just found the centripetal acceleration, and we're told in the problem that the radius of the circle is 10 meters, so we just need to solve and take the square root. So I'm going to plug in for acceleration, which is 25 meters per second squared. That's equal to the tangential velocity squared, which we don't know. We're trying to find it, so we're going to leave that as a variable. We divide both sides by the radius, which is 10 meters. To get v sub t by itself, we're going to multiply both sides by 10 meters. The meters will cancel out, or 10 meters will cancel out. We'll be left with vt squared is equal to 250 meters squared per second squared. So you have meters times meters, which gives us meters squared. Divided by seconds squared. So we take the square root of both sides. We see that our units will be dimensionally accurate. So we have meters per second. He's getting in trouble there. And we got 15.8 meters per second is the maximum speed in which that object can move around the circular path without the string breaking. Okay, so the second question on that form is fairly similar, except in this case, they gave us the tangential speed. And technically, we need to find, oh, the question got cut off, hold on. There we go, that's better. So we're given the tangential velocity in this problem. Last problem we were asked to solve for that tangential velocity. And this time we're looking for the acceleration. Okay, so we need to find the acceleration given the tangential velocity and the radius. So we're going to focus on that second question, or second equation rather, that we looked at, which related the centripetal acceleration to the maximum velocity. So we're going to take the tangential velocity squared and divide by the radius to find our centripetal acceleration. So we're told that the object's speed is 18 miles per hour, and they convert to meters per second for us. Thankfully, it's nice of them. So we're going to take 8 meters per second square it, and divide by the radius. which is a whopping 7.4 meters. And when I say they, these problems are coming from your textbook, but to make life a little bit easier, instead of you having to rummage through your book to find the problem, just typing them into a Google form for you. So yes, that's who they is, your textbook company. So when we square 8, we get 64. We're going to take 64 and divide by 7.4, and we get 8.65. Our units are going to be meters per second squared. And I'll show you dimensionally how those cancel out in a second. Okay, so looking at our system of units here, we have meters per second, and we're going to square that. So we have meters squared per second squared, and we're dividing that quantity, or that system of units, by meters. One of the meters will cancel, and we'll be left with meters per second squared, which are the units for acceleration. So we know that dimensionally, our answer, our response, is accurate. Alrighty, so those are the two problems from the Intro to Uniform Circular Motion exit ticket. I'm going to quickly review one more question from the Google form that was assigned on Friday, which was based on Thursday's video. Okay, so last problem, an athlete runs 4 laps or revolutions around a circular path. What is his change in angular position in degrees and radians? So let's start with part A. So what we're given, right, is the change in position, which we use the variable delta theta to represent, is equal to 4 revolutions or laps, right? Those are synonyms for the same definition. So we have 4 revolutions. We need that change in position in radians and degrees, so we need to convert. Okay, so we need revolutions in the denominator, and we'll start with radians. Okay, we need radians in the numerator. So we know that there are 4 pi radians in every revolution. So we're going to multiply by 2 pi. Sorry, it's Friday. You guys are going to be watching this on Monday. It's Friday to me. For me, I have a Friday brain. So you have a 2 pi up here in the numerator. Okay, so you have 2 pi radians for every 1 revolution, or 1 cycle. So to multiply by 2 pi, we can again leave this in terms of pi or decimal. Doesn't technically matter. So we'll have 4 times 2 times pi. Make sure you put a multiplication sign in between the 2 and the pi in your calculator. And we'll get 25.1. Our revolutions will cancel, and we'll be left with the units of radians, in which we abbreviate as RAD. Okay, next step in part A is we need to then convert the angular position, delta theta, to degrees. So we're going to take 4 revolutions, and we're going to convert. So we're going to multiply by 360 degrees and divide by 1 revolution. And we get 1,440 degrees would be the change in the angular position around the circular path. Okay, for part B, we're asked to find the arc length. So technically, this question can be worded as the circumference, okay, or the arc length. So we want the distance around the outside of the circle that is traveled during these 4 laps or these 4 revolutions. So to find arc length S, right, technically we want 4 times the circumference, okay, or the outer path times 4. The equation that we know for arc length is determined by taking the change in the angular position and multiplying by the radius of the circle. Remember that that change in angular position, delta theta, must be in radians, or we will not get the correct units when we multiply across in this equation. So from part A, we're going to use delta theta, in which we measured in radians, and the radius of our circle, which is given to us in the problem. So we're going to take 100 meters and multiply by 25.1 radians. Radians are an implicit unit, so we multiply by meters. We'll be left with just meters, which is exactly what we want. I would not want to be running this arc length today at 80 degrees outside, so not an ideal distance here to have to run on a day like today. But when we multiply across, we will get 2,510 meters. So less than 2 miles. Okay, but it is a hot one out there today. So that is our arc length. Okay, 2,510 meters. Remember that the change in angular position must be measured in radians when using the arc length equation. The arc length is the distance around the circular path that the object or the person has traveled. All right, so that's it for homework review. I will talk to you in my next video.